All right, let's dive into a real classic today. We're going to tackle a legendary problem from I.E. Irodov's book, one that has been a real headache for physics students for years. It looks simple on the surface, but trust me, it's hiding a really cool secret about the planet we're standing on.
Okay, so here's the deal. Imagine you're the best sharpshooter in the world. You aim your rifle perfectly, dead on, pointing due north. Your rifle is flawless. And, get this, we're even told to ignore air resistance. It's a perfect shot in a perfect world.
So, seems pretty straightforward, right? You aim at the line, you fire a perfect shot, there's no wind, where's it gonna land? The obvious answer is right on the line. But come on, if it were that easy, would we even be talking about it?
That's right. The very first thing you have to understand to solve this problem is that your gut feeling is totally wrong. This perfect shot, well, it's gonna miss.
Yep, you heard that right. This is the whole mystery. Even with perfect aim, a perfect rifle, and no air, the bullet lands off the mark. And figuring out why that happens is what this is all about. It's a deep dive into how things really move on our spinning planet.
So to get our heads around this, we need a totally different way of thinking. You have to stop picturing the ground as being still. The best way to think about it is that you're standing on a giant, super slow-moving carousel. And that carousel is Earth. You know, in physics, we talk about these things called reference frames. An inertial one is just sitting still, not accelerating. Newton's laws work perfectly there. But we live in a non-inertial frame because the Earth is always spinning, always accelerating. And when you're in a spinning frame like ours, you have to invent these fictitious forces to make the math work out. They're not real forces like gravity, but their effects, oh, they're absolutely real.
Think about it like this. Imagine you're on a merry-go-round, and you roll a ball perfectly straight to your friend across from you. To you, on the ride, it's going to look like the ball curved away, but someone watching from the ground would see something different. They'd see the ball go straight, and you were the one who rotated away from its path. That apparent curve, that's exactly what's about to happen to our bullet.
So this phantom force, this ghost in the machine, it actually has a name, and it is the one and only culprit behind our whole mystery. Let's talk about the Coriolis force.
Now, the Coriolis force isn't a push or a pull from anything. It's not magnetism, it's not gravity. It's simply an effect that shows up because we're in a rotating system. But even though we call it an apparent force, its effect on where that bullet ends up is very, very real.
And here's what it looks like in math terms. Don't worry, it's not as scary as it looks. All it's saying is that the force depends on the bullet's mass, its velocity v, and the Earth's spin speed omega. The most important part is that little x in the middle. That's a cross product, and it's a fancy way of saying that the force is always going to be at a right angle, perpendicular to both the bullet's motion and the Earth's spin. And there's a cool trick for figuring out which way that is.
Okay, everybody, do this with me. Seriously, it helps. Take your right hand, point your fingers in the direction the bullet is going, straight north. Now, curl your fingers towards the Earth's axis of rotation, which for us in the northern hemisphere is kind of up and away from the ground. So you curl them up. And where is your thumb pointing? To the right. To the east.
So what did we just figure out? It's simple. In the northern hemisphere, anything moving over a long distance gets a little phantom push to its right. So our bullet, aimed perfectly north, is going to get nudged to the east.
Okay, great. We know what's pushing the bullet, and we know which direction it's pushing. So now for the big question, just how much does it get pushed? For that, we gotta run the numbers. And don't worry, the calculation is actually pretty straightforward. We'll just break it down into 3 easy steps that you've probably seen 1,000 times in mechanics. First, how long is the bullet in the air? Second, what's its sideways acceleration? And third, we just put those two together to find out how far it moves sideways. Simple.
So here's all the info we were given in the problem. Now take a look at that omega value, the Earth's rotation. That's a tiny number, right? It seems crazy that something so small could have any effect at all. But as we're about to see, over a kilometer, it really adds up.
Okay, step 1. Easiest part of the whole thing. How long is the bullet flying? Well, that's just the distance divided by the speed.
And there it is, just over 1 second. So this whole cosmic drama with phantom forces and rotating planets, it all happens in about the time it takes you to snap your fingers.
Now for the acceleration. This formula is pretty simple, but here's the part where people almost always trip up. You see that sign of phi at the end? That is so important. That term is there because the effect is strongest at the poles and weakest at the equator. At the equator, you're just being carried along. At the poles, you're spinning in place like you're on a turntable. That sine term just correctly picks out how much of that turntable spin is affecting our bullet at 60 degrees latitude.
So we plug in our numbers and we get a sideways acceleration of about 0.113 meters per second squared. That's tiny. It's like 100 times weaker than gravity. It's a whisper of a push, but it's a relentless push that's there for the entire flight.
And for our final step, we just pull out one of our trusty old kinematics equations. The distance moved is just 1/2 times the acceleration times the time squared. We've got our A, we've got our T, let's do it.
All right, this is it. We've wrestled with rotating frames of reference, we've decoded phantom forces, we've run the numbers. So, after all of that, how much does our perfect shot actually miss by?
About 7 centimeters. Wow, less than the width of your hand. All of that mind-bending physics, all that talk about a spinning Earth, and it all boils down to a miss of just a few centimeters. It's pretty amazing when you think about it. So let's just wrap this all up. The bullet hits about 7 centimeters to the east, to the right, of where you aimed. Why? Because of the Coriolis effect, which is just what happens when you're moving on a spinning object. And the real lesson here is that our everyday intuition can really fool us in physics. We're all passengers on this giant carousel, and once you start looking closely, you can see its effects everywhere. And that really leaves you with something to chew on, doesn't it? If this gentle, almost unnoticeable phantom force can push a speeding bullet off course by 7 centimeters, imagine what that same force can do when it has hundreds of miles and days to work on a giant mass of air. That's right, this tiny effect is the very reason hurricanes spin the way they do. It's a beautiful example of how the same physics rules our entire world, from a tiny bullet to a massive storm.